Hi guys, so this is going to be a quick video explaining the solution to problem number 4 from the practice exam. A lot of you guys have been asking me for help on this one, so I'm just going to make this video to try to help everyone out. So we're given this surface right here defined as a multivariable function of x and y, and you don't need to know how to sketch this, but you need to be able to visualize what you're being asked to find for parts A, B, and C. So let's start with part A. Part A is asking us to find the tangent to the curve of intersection of the surface with the plane x equals 1 at this point. So we have our surface. So this is not what the surface looks like, but I'm just going to draw an arbitrary surface. Okay, and these are coordinate axes. And we have the plane x equals 1. So the plane x equals 1, which you do need to know how to graph, is going to be normal to the x-axis. And it's going to intersect the x-axis at x equals 1. So it's going to cut into our plane like this. And there's going to be a line of intersection. Okay, so our plane is a surface. So every point on the plane that is also contained in the surface will form this line right here. Okay, so that's our line of intersection. And we're being asked to find the tangent of that line at the point P. Okay, so we want to find this tangent. And to do so, we're going to have to take some derivatives, right? So we need to think about which derivative we need to take in this case. If you look at the plane x equals 1, you can see that the plane extends in the y and z directions, right? It's normal to the x-axis, but it goes in the direction of the y-axis and the z-axis. Therefore, the slope of any tangent on the intersection between this plane and the surface will be given by dz dy. Okay? So, to explain again, because this plane of intersection goes in the direction of the y and z axes and is normal to the x-axis, dz dy will give us the slope of any tangents to that intersection curve. Okay, so to find dz dy, we take the partial with respect to y, so we hold x constant, so our x squared goes away, we get 2y minus 3x. Okay, and so now we need to find dz dy at our given point, which is 2 times 1 minus 3 times 1, which is negative 1. Okay, so we have our slope. Now the next step in this problem is to convert this slope to a vector, because one instruction that was given to you in this problem was to find parametric equations for these lines, not equations using x, y, and z. So to do that, we need two things, right? We need our point and we need our direction. Our point we already know because it's given to us, and our direction we can get really easily from our vector. Sorry, not from our vector, from our slope. Okay, since we know our line is going in the YZ direction, okay, because it's on the plane normal to the x-axis, we're not going to move in the x direction. Our y direction represents our run, so run as in rise over run, and our z direction represents the slope. Okay, so this vector here just means that if you travel 1 unit in the y direction, you're going to travel dz dy units in the z direction because that's the slope. Okay, so you have your point and you have your direction, so all you have to do is combine them into a parametric equation. And I'm going to shift these down a little bit to give us more space. Okay, so if you remember parametric equation for a line, is formatted as r of t is equal to r naught plus v times t. And in this case, r naught is our point, and v will be this vector, so 0, 1, -1, because that's dz dy times t. And so the final answer for the vector equation will be 1, 1 plus t, -1 minus t. And in parametric format, you take each component and you write it separately. So x equals 1, y equals 1 plus t, and z equals -1 minus t. All right? So that's how you solve part A. Now let's move on to part B, for which we're going to use a very similar approach. So again, let me make a sketch of our arbitrary surface here. But now, instead of having a plane normal to the x-axis, we're going to have the plane y equals 1, which is normal to the y-axis. Okay? And so our plane would look something like this, where this is the intersecting curve. And the slope of this curve now, since the curve is on a plane that goes in the x and z directions, will be dz dx. Okay? Our y is not changing, so we're not going to have dz dy. Okay? The two things that are changing are z and x, so the slope of that line will be dz dx. And we can get dz dx by taking the partial derivative. So y is constant, x is our variable. We got 2x minus 3y. And so we need to find dz dx at our given point. And that gives us 2 times 1 minus 3 times 1, which happens to also be -1. Now we need to find our point and our direction for our equation of the line. Our point is the same, and our direction. Now in this case, we're moving in the x and z directions, so our y component of direction will be 0, our x component will be 1, and our z component will be dz dx. And again, that's because for the tangent of this line, if we move delta x, our delta z will be dz dx. So if our delta x equals 1, then our delta z will be dz dx. So we have our point, our direction, and we just put them together. And our vector equation would be our point plus our direction times t, which equals 1 plus t, 1, -1 minus t. So our parametric equations will be x equals 1 plus t, y equals 1, and z equals -1 minus t. Okay? So we have our answers to part A and B. And part C wants us to find the plane determined by the two tangent lines. So we have two lines. We know their directions. If we want to find the plane determined by those two vectors, we need to find the normal vector. Okay? So we have our two directions, v1 and v2. And if we cross them, we can get the normal vector for our plane. And that plane will contain both of those lines. So we know n will equal the cross product of the two directions. And if we look back at our equations for the lines, this is v1 and this is v2. So we cross those two vectors. And that gives us a new vector, which is -1, -1, and -1. Okay, and now that we have our direction, remember any plane needs a direction and a point. Our point will be the point contained by those two lines, which we know will be this point because both lines contain that point. So that's also going to be a point on our plane. And from our definition of a plane, we can construct the equation of a plane, which is -1 times x minus 1, -1 times y minus 1, -1 times z plus 1 is equal to 0. And you can simplify that as much as you want. If you simplify it fully, you'll get x plus y plus z is equal to, let me think for a second, 1 plus 1 minus 1 is equal to 1. Okay, so that will be the equation of the plane determined by the two tangent lines. And that concludes our discussion for problem 4. Hopefully that clarifies you guys' questions. So if you need any more help, just shoot me an email and I'll be happy to answer your question. Happy studying.